In this video, I am going to talk about Oersted experiment. In 1820, Oersted experimentally find that a current carrying conductor can produce a magnetic field. A very simple but a very powerful experiment. So as we know that we have stationary charges, positive charge and negative charge. So if you have a stationary positive charge, it's going to produce an electrical field which is really going outward. This is a positive charge. This is the electrical field produced by a positive charge. If I have a negative charge, then the field produced by the negative charge is really inward. So basically the electrical field produced by positive and negative charge is nothing but the path followed by test charge around them. So it is nothing but the path followed by the test charge around these charges. Test charge means a unit positive charge. So if I put a unit positive charge close to a positive charge, this is going to repel it. And if I put a unit positive charge close to a negative charge, it is going to attract it. So that is the direction of the electrical field. Remember, the electrical fields are not closed curves. So this is the electrical. But if these electrical charges comes into motion, then they also, in addition to the electrical field, they can produce magnetic field. And that's what Oersted found experimentally in 1820, that a current carrying conductor, when the current is allowed to flow through a wire, it also, in addition to the electrical field, produces a magnetic field. And how did he find it? He used a magnetic needle placed close to the current carrying wire, and the magnetic needle shows a deflection. I'm going to replicate that experiment. And what I'm doing for my experimental process is that I'm going to take 2 batteries. You can take 1 battery. Just because I didn't have a powerful one. And then I'm going to connect it to a switch. And then I'm going to connect it with a wire, long wire. As soon as this switch is closed, when I press this switch, the current is going to flow from this direction to this direction, from the positive terminal of the battery to the negative terminal of the battery. So this is the direction of the current that is flowing into it. Now, when the current flowing into this one, this not only produces the electrical field, but produces a magnetic field. So what I'm going to do, I'm going to bring a magnetic compass close to it and then see if this magnetic needle can be deflected by the current which is flowing into this wire. A very simple experiment done by Oersted in 1820 that led to many things. In 1831, in fact, Faraday was able to do a reverse process that if a current carrying conductor can produce a magnetic field, why not a changing magnetic field can produce an electrical current? Or why not a mechanical energy can be converted into electrical energy? I want to show you the experimental setup that I did for that. What I need, I am using 2 batteries. I'm using a switch. I'm using some crocodile clip wires. This is the wire through which I'm going to allow the current to flow through, the magnetic needle, and a magnet of the wire. The other terminal of the wire is connected with this end of this switch. Sure, it's going to work. And I'm going to have this compass needle. Now in this situation, you can see that the switch is not on, so there's no power, there's no current that is flowing through it. The current is going to flow through this positive terminal and going back into the negative terminal, so it's going to be flowing like counterclockwise direction. So this magnetic needle can only be distracted, or I can show it, this can only show deflection when you bring a magnet close to it. So you see that this, when the magnet is close to it, is showing the deflection, right? Now I'm going to move the magnet away, totally away out of this field, and I'm going to have this needle rest, completely come to a stop. Once it comes to a stop, then I'm going to allow the current to flow through this wire and then see if that can produce some deflection. If there is a deflection, then it means then this current carrying wire also produces the magnetic field. So you see there's a clear deflection when I allow the current to pass through. When I open the switch, again it comes back to its original position. There's a clear deflection. So it means this current carrying wire, besides producing an electrical field, is also producing some kind of magnetic field around it, and that is why that can be shown with the help of this compass needle. That's what Oersted did in 1822 to establish or found that there is a magnetic field produced by a current carrying wire. So if I come to the direction, how do I find the direction of this magnetic field? So this is my experimental setup. This is my experimental setup. I have this battery, first battery, second battery, and then it's connected to the switch, and this is connected to this wire. As soon as I press the switch, the current is going to flow in this wire in this direction, and a magnetic field is produced. Let's say I want to find out, this is the magnetic field. Let's say at this point P, I want to find out how much is the magnetic field and what is the direction of the magnetic field. So first the direction. So in order for me to find out the direction of the magnetic field, I like right hand rule, in which if I stretch my thumb of the right hand in the direction of the current, and I point my fingers towards the point where I need to find out the magnetic field, then the direction of my palm will represent the direction of the magnetic field. So magnetic field at this point is vertically inside the plane of the paper. So this I'm going to write with a cross. So magnetic field here is vertically inside the plane of the paper. If I bring this compass needle on this side, then the direction of the magnetic field will change. And that can be, let's say this is a point P prime, and I want to find out the direction of the magnetic field at this point. Then again, I'm going to use my right hand rule. I'm going to stretch my thumb in the direction of the current and my fingers towards. I can do it this because my direction of the current is not correct, because my thumb is pointing in the downward direction, whereas current is flowing in the upward direction. So I have to flip my hand. So I'm going to put my fingers in this direction and this thumb in the direction of the current. And I will see that the direction of the magnetic field at this point is vertically outside the plane of the paper, vertically inside the plane of the paper at this point, and vertically outside the plane of the paper. The direction of this magnetic field actually is determined with using this convention of arrow. So when you see an arrow going away from you, you will see the rear end of the arrow, which is just a cross. So this is like a cross going inside. When you see an arrow coming towards you, you will just see the tip. So you will see a magnetic field vertically outside. Now, how much is the magnet? This is the direction of the magnetic field. The next question is, how much is the magnetic field that is produced at this point, or how much is the magnetic field that is produced at this point? And that is given by Biot and Sever, two French scientists that worked on it and gave how much, calculated how much is the magnetic field which is at this point P or P prime, or due to any shape current carrying conductor. So in the next video, I'm going to talk about the Biot and Sever law, how to find out the magnetic field at the point P, and then using the Biot and Sever law concept, how can we further define and find the magnetic field due to a straight current carrying conductor.